Hello, welcome to this talk on zooming in on a black hole. This talk is meant to tell you about the event horizon results that are to be announced today, Wednesday, April 10th, 2019. Event Horizon Telescope collaboration has announced that they have taken a very high resolution picture of the central black hole that resides within our own galaxy, Milky Way, and these results are important. So this talk is sort of meant to tell you what we expect from the results, what they would be like, why they're important, and how they're doing it. So these three parts will this talk address. So moving on, that's the announcement from Event Horizon Telescope that there's a media advisory first results from the Event Horizon Telescope to be presented on April 10th. So, and they're holding multiple press conferences, as one can see. Now, to understand what it is all about, uh, let's sort of split it into two parts. So we have Event Horizon Telescope. First part is Event Horizon. Event Horizon is something which is related to a black hole, and a telescope. In this case, they're using a radio telescope. So the Event Horizon Telescope is an international collaboration aiming to capture the first image of a black hole by creating a virtual Earth-sized telescope. These are two parts. So to understand further, we go ahead and ask ourselves, what is a black hole? How do they form? And have we observed them in the past, previously, before this one? So as to understand what this one would be like. Now, in order to know what is a black hole, we need to look at the star cycle. So a typical star cycle, stars are born and stars die, they live through. So that's the typical star cycle, which is being shown here. The star formation takes place as a nebula, as a gas of clouds, mostly hydrogen alpha, uh, um, mostly hydrogen, hydrogen and helium gases, which collapse thermally and form stars. Simplest example, which is a nearby example, is of the Orion Nebula, which is an active star-forming region. Um, Once these stars are formed, they live through their life, and the main sequence star, where the nuclear reaction sort of sustain it, is like the middle at the middle of the slide, and the example there is our own sun. Our sun is a main sequence star. It's at the middle of its life cycle or star cycle. Once the star burns through its middle life cycle, it has choice according to its mass whether it can go into two branches. So one branch is the red giant branch, the lower one here, and it can end up as a white dwarf. That is when the mass of star is less than four times the solar mass. If the star is way more massive than our sun, so our sun is kind of like a ballpark standard. If a star is way more massive than a sun than our sun, then it becomes a supergiant. It expands, and supergiant star finally goes off, explodes into a supernova, and settles down into either a neutron star or a black hole. Now, an example of supergiant is in the constellation of Orion. So if you can see here, that is the constellation of Orion, and the yellow star there is Betelgeuse. It's 900 times the mass of Sun and 640 light years away. That's a red giant star, a super red giant, and Betelgeuse is supposed to go supernova or explode anytime. That can happen anytime, and in fact it would already have happened. We would not have known it. We would only know it when light comes to us from it. So it would have happened maybe 640 years back. So anytime it can go supernova. So that's one of the super red giant stars, and it will go supernova, and eventually it will also form a black hole. So that's the star cycle, which the star goes through and forms a black hole. Usually we don't represent star cycle like this, but rather astronomers use what is called the HR diagram or Hertzsprung-Russell diagram to label the stars where they are in their star cycle. Typically this is the luminosity versus the surface temperature diagram. So one can see Sun is in the middle, and then Betelgeuse is at the end in supergiant phase. So that's the kind of a thing. Now, what is all this got to do with? Of course, the main driving force behind everything here is gravity. So gravity is the one which is taking the stars from nebula stage to a black hole. And the theory of gravity at present is the general relativity or general theory of relativity given by Einstein, the field equations. His famous field equations are sort of kind of a graffiti here. But just to simplify, as the essence of the field equations is that geometry, space-time, or gravity is a manifestation of geometry of space-time, and it results from this. The source of geometry is matter. So matter tells geometry or space-time how to curve, and in turn, geometry tells matter how to move. So that's the kind of a relation of or manifestation of gravity in general relativity. And it was precisely shown in this animation, which I'll play it again, of a water drop falling on and creating waves, something like this. So think of space-time as a fabric, just like the screen, and any disturbance which goes on the fabric due to matter creates ripples or disturbances in space-time. So that's the relation. That's the way gravity is in Einstein theory. And one thing which gravity respects and general relativity respects is the causal rule or special relativity, that light travels at 45 degrees in space-time on a space-time diagram. So it's for instance, you can see in the top right corner, um, there's a flash of light, and as the flash spreads, it spreads evenly in all directions in space, and a split second later, it's a circle because I've drawn it as two dimensions, and a split second after that, it's a bigger circle. So essentially, going on to the left, light is moving in a kind of a cone-like structure if drawn in a space-time diagram where time is the vertical axis. So, and gravity also sort of respects that, at least locally, at every point in a space-time. Locally, light has a light cone-like structure, so the light moves at 45 degrees. What this means is in the bottom right, for instance, causality. Like suppose there would be a death of sun at any point, and Earth is outside the light cone of that. We at Earth will not know that there has been a death of sun only until Earth enters the light cone of the sun. That is the light which has left, the final ray of light which has left at the depth of the sun, and that reaches us, or we enter that light cone equivalently after 8 minutes. So that's the idea, and general relativity respects that. So that's an important thing, which will be important in the event horizon picture. What event horizon is. But moving on, any theory in science or model needs to be tested, and general relativity is also a model or a theory, and it gave certain predictions, and it were tested. Like for instance, if for instance consider in our Earth Sun system, suppose there's a star which is behind the sun. We cannot directly see it, but it's very near the sun. Now, if light is coming from that star to us, going very near the sun, light gets bent when it passes near the sun. This results in an apparent image of star forming, which is shifted from its actual position. And this effect is predicted by Newtonian gravity as well, the bending of light, and Einstein's gravity. The difference is a factor of 2. And that factor of 2 was a deciding factor in the 1919 British eclipse expedition, which decided that Einstein's model is the correct one here. So one can go ahead and read about it here. However, even further, it's not just with the sun that this experiment was done. This thing was also observed for galaxy clusters. So this image is of a galaxy field. In the center, one can see there's a massive galaxy. Now, when there's a massive galaxy and behind it is some bright object, like a quasar or something, light coming from that particular object bends around this galaxy in the center when it reaches us, and it becomes something like a lens. This is called gravitational lensing. The gravity of the massive galaxy within bends the light from the cluster which is behind it and forms the image of the cluster, or image of that bright object around it, like a ring which is being shown around that center. So that ring forms around the center, which is being shown here, and these rings are called Einstein rings and have been predicted by general relativity. So that's an important thing. And now, coming back to black holes or the star cycle, we see that gravity holds a star together. However, because a star is burning a nuclear fuel, a total collapse is prevented by thermal and radiation pressure from inside. So the star is kept in equilibrium during its life cycle, the early life cycle. Like for instance, sun is in equilibrium; it's not collapsing. But however, with time, it ends, and the pressure collapses, and gravity makes the star collapse. It explodes, forms a supernova, and then finally settles down, accreting its own matter into a phase called neutron star, and a neutron star finally settles down as a black hole with matter accreting around it. Also, there could be a configuration of, so these black holes are called stellar black holes, which are a result of star death. And there could also be a configuration where there are two stars in a binary system. One star has collapsed to form a black hole, and there is a second star nearby. The black hole accretes the matter from the second star, forming an accretion disk shown here, and this accretion disk makes a particular jet-like structure which can be seen. And there are various examples of this. For instance, one of the examples is Cygnus X1. You can see the optical image of that here being zoomed in. Cygnus X1 is an X-ray binary. So the stellar black holes, the accretion disk radiate in X-ray. The jets are often seen in radio. So that's the frequency of the electromagnetic spectrum where we can see. So that's the X-ray, Cygnus 1 in X-ray. So these are stellar black holes. Now, stellar black holes have, so this is sort of like an indirect evidence, one of the indirect evidence that there are black holes existing out there. There is also even another evidence of black holes being there, which was the gravitational waves that were observed, and from a merging black hole. So suppose we have two black holes and they're going around each other and they finally merge to form a bigger black hole. This merger is again a disturbance in space-time, much like I showed earlier the animation. And whenever there's a disturbance in space-time, it sends off gravitational waves. And these gravitational waves were detected by LIGO observatories, two LIGO observatories in the United States, one at Hanford and one at Livingston. And one can see the smoothed line here is the numerically calculated waveform from general relativity, and the observed lines sort of agree with it. So Einstein's gravity is sort of agreeing to the And these smoothed lines were the numerical simulation of two black holes merging. So therefore, one sort of is confident that the waveform is actually coming from two binary black holes orbiting and merging, orbiting around each other and then finally merging. So that's an example of a black hole. Just to give you another go ahead. Actually, there was I wanted to put in the sound of gravitational waves here, but one can go in. There are a lot of videos where one can check out how do gravitational waves, when they convert it to sound, they sound like. But that's okay. That does show here, but I'll just skip ahead. So this diagram sort of reflects what are the known stellar black holes in a sort of what kind of masses of stellar black holes are known. For instance, these are black holes which are around 1 to 2 solar masses, and then these are stellar black holes which are from 5 to 80 solar masses. So they're not really very heavy black holes, but these are sort of medium level black holes. I mean, these are going up till 40 to 80, between 40 to 80 solar masses. So these were the objects which were observed by LIGO, for instance. These two black holes, they were orbiting each other, and then they combined to form a bigger black hole. Same with this. And of course, these are the neutron stars here, for instance. And neutron stars, there was another event where two neutron stars combined and they formed another object. We're not sure what object that is, so it's just that. However, these are black holes of 5 solar masses and above. So that tells you the picture that the stars which are of solar mass 1 to 2, they end up as neutron stars, and massive stars which are more than solar masses end up as black holes. However, the black holes which the Event Horizon Telescope is interested in is at the center of our galaxy. So those type of black holes are referred to as galactic black holes. So these are a different kind of black holes. They are also supermassive black holes. These black holes come at the center of our galaxies. They're at the center of our galaxies, and these can be million solar masses. That's the huge number here. And therefore, these are the driving engines of our galaxies, how the whole galaxy works as a whole. Now, so these are some of the images which have been taken by various telescopes combined in different bands. For instance, this one image is taken by Hubble Space Telescope of a black hole. There's a galaxy here, so this galaxy is over here, and there's a supermassive black hole there. Now, look at the structure which is forming from this region. There's a jet, and this is a 5,000 light year long jet ejected from the active galaxy M87, and you can see the color is the yellow here, and the jet is blue in color. So that means there's a different wavelength which is being radiated. It's actually blue synchrotron radiation. It's usually in radio. Synchrotron radiation comes, the jets are in radio. There's another example of a radio galaxy, Hercules A, where there's these two jets in two different directions, opposite directions, so far away from the main galaxy where the source is. This tells you the sheer power of these supermassive black holes. There's another one here, Centaurus A. Now, just to show that this is a composite image of various wavelengths. So, for instance, this is the radio, and then this is the infrared, optical, X-ray, radio, hydrogen, infrared, optical, X-ray. So X-ray and radio is sort of something which is giving you telling you about the jet and it's the jet structure. It's primarily coming from X-ray and radio emission. That's why X-ray and radio emissions are required. Rest of the galaxy is, of course, optical and hydrogen alpha, or IR. IR is the dust which is there in the galaxy. So moving on. Now coming back to what actually is the event horizon here in these black holes. So whenever a black hole forms For instance, suppose let's take an example of a stellar black hole which is forming due to a collapse of a big star, big massive star, more than solar masses. Uh, Whenever a star forms, there's a statement in general relativity which is referred to as the weak cosmic censorship. It's a statement that a space-time singularity arising from a gravitational collapse of reasonable matter must be shrouded by an event horizon. So that the statement was given by Roger Penrose. That is, whenever a collapse takes place, the collapse ends up in a configuration where there's a singularity at the center, and the singularity is surrounded by an event horizon. Now, what is this event horizon? Let's remember that those light cones which I talked about, whenever the black hole forms, what happens is that as if it forms a region of space-time such that uh, if you're far away from that region, the light cones are perfectly erect. So you can see this time is vertical and space is horizontal. And as you go near the black hole, these light cones start tipping over. And it's important that everything which moves, it moves inside a light cone. There's nothing can move outside a light cone. Okay, so since these light cones tip over, anything which has to move will only have one direction to move, that is inside. So you can only move inside, they can't move outside. Okay, so another thing is, so on the right, if you see on the right, so what it shows is if we draw this picture in slightly different coordinate system, in GR, general relativity, one can choose different coordinate system for our geometry, much like we choose plane, if we choose to work with plane polar coordinates on a plane, or Cartesian coordinates. So we can choose a different coordinate system, and in this different coordinate system here, one can see this horizon, which is r equal to 2m line, is actually a 45-degree line. So this is the important thing. So it's actually a line of light. It's also called a null surface. So whenever there's a collapse happening, nothing therefore can go out, because that's a 45-degree line. And 45-degree line, we know, are boundaries of all possible time-like trajectories. Every material object or causal influence is inside a light cone. So therefore, this event horizon is essentially a surface around a black hole which acts like a one-way membrane. Things can fall in, but nothing can go out. And so these are also, again, predictions of general relativity. Now, the engine of our galaxy is Sagittarius A, which is the target, one of the targets of Event Horizon Telescope. The best observations of Sagittarius A using very long baseline interferometry radio astronomy have determined that it's approximately 44 million kilometers across this region, and which is just distance of Mercury to Sun, and it contains 4.31 million solar masses. So that's how large it is. Now, since it's a black hole, we cannot see it because light cannot come out of it. How do we know that this region has a black hole? Is by an extensive study of looking at the orbit or the movement of stars in that region. So the figure on the right shows the orbits of various stars in that region, which was observed over a very long period. So it's like 16-year observation of stars in that region. It shows that there is, and one can calculate what's the mass within the system, which is making these orbits possible. And that gives you that this mass is around 4.3 million solar masses. So that's the Sagittarius A region within our Milky Way. So there's a black hole residing within our core, okay? And here the Event Horizon comes in, Event Horizon Telescope comes in. The Event Horizon Telescope's image of the Milky Way's Sagittarius A, also called SGRA star, is expected to capture the black hole's shadow on its accompanying disk of bright material. So there's a bright material around it, and the gravity, because it's intense near a black hole, the disk's light will be warped around the event horizon of the black hole. As I mentioned, gravity bends light. So gravity of that black hole, which is so intense, it'll bend it around and it'll form again a ring-like structure. This ring will probably be asymmetrical because gravity will bend light from the inner part of the disk, which is towards Earth, more strongly than the outer part, which is away from Earth. So making one side appear brighter in a lopsided ring. So the simulation is shown on the right. Now, the question, what type of questions we are asking here? One is, does general relativity hold up close to a black hole? The exact shape of ring here, which will be forming, which tell us whether how much can we trust general relativity. Because you see, these are extremely strong gravity regions. These are the strongest gravity region possible, a black hole. And a theory is sort of being tested to its extremes. One of the reasons why this is important is that at when near it's a sort of expected that near black holes where gravity is strong, there's another theory which is quantum mechanics comes into play. So these two theories at the moment are sort of not reconciled properly. We don't know how they work. So that is the final goal in theoretical physics, to know what quantum gravity is, how gravity works according to principles of quantum mechanics. We don't know that. And the best place to find out are the black holes, because gravity is very strong there and quantum effects come into play. So that's sort of, but I still say event horizon would not really answer what would be the quantum effect be like, but it is important as far as to know whether general relativity is valid near a vicinity of a black hole, or general relativity is valid to describe a black hole, because uh, there could be 12,000 different black hole shadows which could differ from Einstein's predictions. So this would tell whether general relativity is being modified near a black hole or it stays the same. Then we have a question, do pulsars surround the Milky Way's black hole? That's another way to test general relativity. For instance, if there's a pulsar which is a rapidly spinning stellar object or a neutron star, it sweeps the sky with a beam of radiation. This beam of radiation, any light is, as I mentioned, light is bent by the gravity. So since light is bent by gravity, it changes frequency, and that causes gravitational redshift. If there are pulsars near that black hole, observing the gravitational redshift of those pulsars would tell us more about general relativity, or would be a precise test of general relativity. Then there's a question, how do some black holes make jets? Remember, I mentioned this particular galaxy where there's a jet which is 5,000 light years away from the main galaxy, main source. Um, Although the central black hole in our own galaxy is quiet, which is a surprise. Why is it radio quiet? Why doesn't it have any jets? This Event Horizon Telescope's other target is the black hole in a galaxy M87, shown on the right. EHT will make a measurement of the magnetic field of this particular galaxy to try to find out why and how this jet is being created, because jets are usually created as a result of electrons moving in a magnetic field, and that is why they gave off a radiation in radio band. So this is something here. So that's why radio astronomy is important. So the radio emission is not thermal, it is produced via a synchrotron mechanism. Energetic electrons spiraling in magnetic fields emit synchrotron radiation, and they give off radio. Now, the atmosphere is transparent in radio band. Approximately, there are some effects from ionosphere, but those are taken away with calibration, just like we would do adaptive optics. Radio astronomy sort of started in 1923. Karl Jansky sort of discovered that his antenna was receiving radiation from outside Earth's atmosphere. He noticed that this radiation appeared at the same sidereal time on different days, and that its source must hence lie far outside the solar system. And further observations enabled him to identify this radio source as the center of the galaxy. So radio astronomy started off. However, radio astronomy, which is the way it's done currently, is referred to as what's called very long baseline interferometry. I mentioned this term before as well. Uh, in a way, what this means is that we don't use just one single radio telescope, but rather an array of radio telescopes to observe. The main reason for using this particular arrangement rather than having a single one is that by using an array of radio telescopes, one can increase the aperture of telescopes to very large extents. And this is something which is being used by the Event Horizon Telescope. What it goes is that if you have, for instance, a simple two antenna radio interferometer, in the sense that it takes a signal and then combines it, find what's the correlation between them. The correlation is sort of like an inverse Fourier transform of the intensity of the source, which is from where the signal is coming from. Now, what happens is the combination of two antennas, so as to say, creates a telescope with an aperture given by the distance, approximately given by the distance between them, which is referred to as the baseline. So in this way, a particular baseline configuration will give us a particular intensity and in particular region of that source. And to get the intensity distribution in that source, we just need to vary this baseline. So this is why, for instance, you see here this is a very large array of 27 radio telescopes. The radio telescopes are often moved around on rails to get different baseline configurations, and also the motion of Earth, the rotation of Earth, allows us to have different baselines so as to image the source completely, or the source intensity distribution completely when it rises till it sets. And this can be done during the day as well. So you don't need nights to do this. That's important. Now, in order to take a picture of a black hole, which is at the center of our galaxy, one needs to zoom in a lot. And one needs a telescope which is of very large size. And one cannot really have that physically. So this is where the Event Horizon Telescope comes in. What it does is it links radio dishes across the Earth, and that creates a virtual planet-sized telescope with a magnifying power capable of imaging black hole event horizons. So for instance, just to show here the telescopes which are linked together, so we're getting observation from 8 different telescopes. Remember, this is a great technological feat, not just in terms of angular resolution, that is of 35 microseconds, equivalent to standing in New York and being able to read the data on a quarter in Los Angeles, but also that the data from 8 different sites all over the globe, different parts of the globe, are being sort of stably distributed to a center where the processing is taking place. So you need a stable transport of data and also a synchronized transport of data from all these observatories. So there's a stability and synchronization which is required to transfer data from these observatories for further processing. And processing also requires a lot of jugglery there. So this is how the Event Horizon Telescope is sort of expected to take a picture of a black hole at the center of our galaxy, and we'll see what it gets. So, and I'll just end it by saying that it's really an exciting time to be doing astronomy and astrophysics at the moment. Thank you.